Picture a time before time, an era so ancient that the universe itself was still figuring out how to glow. This was the cosmic dawn, the moment when the first stars flickered to life, tearing through the darkness and igniting the grand story of everything we know. But here's the thing, we're still piecing together what actually happened during those mysterious first chapters. The more we learn, the more questions we uncover, like stumbling through a cosmic detective story where every clue leads to another puzzle. What triggered those first sparks of light? How did infant galaxies take shape in the void? And what secrets are still hiding in the shadows of this primordial dawn? For decades, scientists have been chasing these answers, peering back over 13 billion years into the past, straining to catch whispers from the universe's infancy. And what they've found is stranger than anything we could have dreamed. Black holes that shouldn't exist yet, galaxies defying the laws of physics, signals from the void that no one can fully explain. This is the cosmic dawn era, a time of chaos, creation, and mysteries that rewrite our understanding of reality itself. And today, we're diving headfirst into 25 of the most mind-bending enigmas from this epoch, each one a thread in the tapestry of our cosmic origins. This isn't just astrophysics, it's a journey to the very edge of what we know, where the rules bend and the impossible seems to lurk around every corner. Because the cosmic dawn isn't some distant abstraction, it's the foundation of everything. The atoms in your body, the light from your screen, the air in your lungs, all of it traces back to those first stellar fires. So buckle up, by the time we're done, you'll see the night sky differently, not just as points of light, but as fragments of a story that's still being told, one mystery at a time. Imagine a universe so young, so raw, that not a single star yet burned in the void. No planets, no galaxies, just an endless sea of darkness waiting for that first spark. Then, somewhere in the abyss, it happened, the birth of the very first stars. These weren't just any stars, they were titans, monsters of pure hydrogen and helium, blazing with a ferocity we can hardly comprehend today. Scientists call them population 3 stars, and they rewrite the rules of cosmic creation. Picture a star not just bigger than our sun, but hundreds, maybe even 1,000 times more massive. Stars so luminous they could outshine entire galaxies we see now. But here's the mystery: how did they even form? Today's stars condense from swirling clouds of gas and dust, but back then there was no dust. No heavy elements, just the bare essentials of the universe, hydrogen and helium, floating in an almost perfectly smooth cosmic soup. So how did these first stars clump together, fighting against the universe's own expansion to ignite? One theory suggests that dark matter, the invisible scaffold of the cosmos, played midwife to these stellar giants. Its gravitational pull might have corralled those early gases into dense enough pockets to collapse under their own weight. Another idea points to sound waves rippling through the newborn universe, creating tiny density fluctuations that snowballed into stellar nurseries. But the truth is, we still don't know for sure. And then there's the haunting part. We've never actually seen one of these stars. They lived fast and died young, exploding in violent supernova after just a few million years, a blink in cosmic time. Their remnants should be scattered across the cosmos, but finding them is like searching for ghostly fingerprints. Some astronomers hunt for their chemical signatures in ancient gas clouds, while others scour the skies for the faintest echoes of their deaths in distant gamma-ray bursts. Every clue we find only deepens the enigma. What if these stars didn't just die? What if some collapsed straight into black holes, seeding the universe with darkness before light even had a chance to take hold? The possibilities twist our understanding of how cosmic dawn unfolded. Because if we're wrong about the first stars, we might be wrong about everything that came after. Now, let's step forward in cosmic time past those first stars into an era where the universe itself underwent a dramatic transformation. Picture this: the cosmos was no longer a dark, foggy void, but gradually became the crystal-clear expanse we recognize today. This pivotal shift is known as the Epoch of Reionization, and it's one of the most hotly debated chapters in our cosmic history. For hundreds of millions of years after the Big Bang, the universe was filled with a thick haze of neutral hydrogen gas soaking up light like a cosmic sponge. Space wasn't just dark, it was downright murky. Then something changed. Powerful sources of radiation began blasting through that fog, stripping electrons from hydrogen atoms and turning the gas transparent. But what exactly flipped the switch? The answer isn't as simple as we once thought. For decades, astronomers assumed quasars, supermassive black holes at the hearts of young galaxies, were the primary culprits. These cosmic behemoths spewed out torrents of ultraviolet radiation, enough to ionize vast regions of space. But here's the twist: recent observations suggest there might not have been enough quasars to do the job alone. Early galaxies, brimming with those massive population 3 stars, could have played an equally crucial role. Their intense ultraviolet light may have contributed significantly to clearing the cosmic mist. And then there's the timeline. Some models suggest reionization happened relatively quickly, wrapping up within a few 100 million years. Others argue it was a drawn-out process, with patches of the universe staying opaque far longer than expected. The James Webb Space Telescope is now peering into this era like never before, spotting galaxies so early that they shouldn't have existed yet, throwing another wrench into our theories. The stakes couldn't be higher. If we misunderstand reionization, we risk misreading the entire story of how structure formed in the universe. Did galaxies light up the cosmos first, or did quasars lead the charge? Was it a coordinated effort or a chaotic free-for-all? Every new observation pulls us deeper into the mystery, revealing a universe far more complex than we ever imagined. Here's the cosmic irony: we're trying to study the birth of light by staring into darkness. The cosmic dawn's first starlight should be visible to us after all. It's had over 13 billion years to reach our telescopes. But there's a catch. That light is trapped behind an impenetrable curtain called the Dark Ages. This was the universe's awkward phase, a murky epoch where space was filled with neutral hydrogen, gas so thick it absorbed starlight like a cosmic sponge. The very first photons, those pioneers of illumination, never made it to us. They were swallowed by the fog, leaving us with a glaring gap in our cosmic scrapbook. So how do we investigate an era whose light went missing? Astronomers have become cosmic detectives, relying on indirect clues instead of direct snapshots. One of their most powerful tools is something called the 21-centimeter signal. Picture hydrogen atoms, the universe's most abundant building blocks, occasionally flipping their internal magnets like tiny cosmic switches. Every time this happens, they emit a faint radio whisper at a very specific wavelength, 21 centimeters. By mapping these whispers across the sky, scientists can reconstruct the invisible structure of the early universe, tracing where gas clumped together before stars formed. But even this signal isn't straightforward. During the cosmic dawn, that 21-centimeter emission didn't just travel cleanly through space. It interacted with the very first starlight, creating a detectable ripple effect. Think of it like hearing an echo in a pitch-black cave. You might not see the original sound source, but the reverberations tell you where the walls are. The challenge: this signal is incredibly faint, drowned out by everything from galactic radio static to human-made interference. Projects like the Square Kilometre Array and the Hubble Space Telescope are racing to isolate it, peeling back the noise to uncover the universe's oldest secrets. And then there's the ultimate plot twist. Some theories suggest we might never detect this signal at all. If the first stars ignited earlier than we think, their radiation could have altered the hydrogen in ways that erase the 21-centimeter fingerprint entirely. It's like a cosmic magic trick. The evidence vanishes right as we're about to grasp it. This missing light isn't just a technical hurdle, it's a reminder of how much we still don't understand about the universe's first chapters. Every workaround we devise only leads to new questions, turning the cosmic dawn into the ultimate cold case. But dark matter, the invisible architect of the cosmos, might hold the key to one of the cosmic dawn's biggest puzzles: how galaxies assembled so quickly in the universe's infancy. Picture a scaffolding made of shadows, an unseen structure weaving through space, its gravity tugging at the primordial gas. Without it, the universe might still be a formless void. Yet how exactly dark matter shaped those first galaxies defies even our most advanced simulations. The problem starts with scale. Modern galaxies, like our Milky Way, sit nestled within vast halos of dark matter, ghostly cocoons that outweigh visible stars and gas by a factor of 10 to 1. These halos act as cosmic glue, holding galaxies together. But in the cosmic dawn, things didn't play out so neatly. The earliest galaxies were tiny by comparison, yet they formed with shocking speed, cramming stars into dense knots far sooner than models predicted. Some theories suggest dark matter behaved differently back then, clumping together more aggressively or interacting in ways we haven't accounted for. Then there's the mystery of feedback. As those first stars ignited, their radiation and supernova blasted surrounding gas outward, fighting against dark matter's pull. In today's universe, this balancing act is relatively orderly, but in the cosmic dawn, chaos reigned. Some simulations show dark matter halos being ripped apart by stellar winds, while others suggest it might have absorbed these shocks like a cosmic sponge, adjusting its distribution to cradle budding galaxies rather than crush them. The most tantalizing clue comes from an anomaly called the cuspy halo problem. Simulations predict dark matter should pile up densely at the centers of galaxies, creating sharp peaks in gravity. Yet observations reveal smoother, flatter cores, as if something erased those dense cusps. One radical idea proposes that early dark matter was slightly warm, meaning its particles moved fast enough to blur those sharp edges. Another suggests interactions with normal matter, perhaps through some unknown force sculpted halos into their current shapes. Every new discovery deepens the enigma. The James Webb Space Telescope has spotted galaxies so compact and bright in the early universe that they shouldn't exist under standard dark matter models. Either we're missing a crucial piece of physics, or dark matter's role in the cosmic dawn was far stranger than we ever imagined. One thing's certain: unlocking this mystery could rewrite not just the story of galaxy formation, but our entire understanding of the invisible framework holding the cosmos together. At the edge of our cosmic maps lies a glaring discrepancy, a cosmic census that just doesn't add up. According to our most sophisticated simulations, the early universe should be teeming with thousands of tiny dwarf galaxies, orbiting larger ones like fireflies around a lantern. Yet when we point our telescopes skyward, we find only a fraction of these predicted satellites. This isn't just a minor accounting error. It's a full-blown crisis in cosmology known as the missing satellites problem, and it threatens to upend our understanding of how structure formed in the infant universe. The roots of this mystery trace back to dark matter. In computer models, the universe's invisible scaffolding crumbles into countless small clumps as gravity works its magic over billions of years. Each of these clumps should have collected enough gas to spark star formation, birthing swarms of dwarf galaxies. Our own Milky Way alone was expected to host hundreds of such satellites. Instead, we've found barely a few dozen. So where did the rest vanish? One possibility cuts straight to the heart of dark matter itself. Maybe our simulations oversimplify its behavior. Typical models treat dark matter as cold, slow-moving particles that clump easily. But if dark matter was slightly warmer, its particles would have zipped around faster in the early universe, smoothing out those tiny density fluctuations before they could collapse into galaxies. This warm dark matter scenario could explain the shortage of dwarfs, but it's not without consequences. Tweak dark matter's temperature too much, and suddenly larger galaxies struggle to form as well. It's a cosmic tightrope walk. Then there's the brutal reality of galactic survival. Early dwarf galaxies weren't just small, they were fragile. Intense radiation from the first stars could have sterilized them before they even had a chance, boiling away their gas and leaving behind dark matter husks too dim to detect. Others might have been cannibalized by larger galaxies, torn apart in gravitational tug-of-wars we're only now learning to reconstruct. The James Webb Space Telescope is turning this mystery on its head by spotting ultra-faint dwarfs we previously missed galaxies so diffuse they're practically ghosts. But even these discoveries don't close the gap. Some theorists argue we're not missing galaxies at all, we're misreading the universe's blueprint. Alternative gravity models, like modified Newtonian dynamics, toss out dark matter entirely, suggesting gravity itself behaves differently on cosmic scales. Yet these theories struggle to explain other observations, leaving us in a stalemate. What makes this puzzle so critical is its ripple effect. If we're wrong about how dwarf galaxies formed, we might be wrong about everything from dark matter's properties to the universe's expansion history. Each missing satellite isn't just a gap in our maps, it's a silent witness to physics we've yet to uncover, hiding clues to the cosmic dawn's deepest secrets. The James Webb Space Telescope was supposed to bring clarity to the cosmic dawn instead. It handed us a cosmic anomaly we can't explain. When astronomers pointed its infrared eyes at galaxies from just 300 million years after the Big Bang, they expected faint smudges, the dim glow of infant stars struggling to ignite. What they found shattered expectations, galaxies blazing with the luminosity of modern cosmic titans, packed with stars that shouldn't have had time to form. These celestial overachievers are rewriting the rules of galactic adolescence, and they've thrown astrophysics into a full-blown identity crisis. At the heart of the confusion lies a simple question of scale. In today's universe, galaxies grow gradually, feasting on gas over billions of years like slow, methodical giants. But these early galaxies, some no wider than the Milky Way's central bulge, somehow churned out stars at rates 10 to 100 times faster than expected. Picture a toddler bench pressing a truck. That's the level of defiance we're dealing with. The sheer intensity of their starlight suggests reservoirs of gas so dense and vast that they defy conventional models of how matter clumped together in the universe's infancy. One radical solution points to dark matter behaving in ways we never anticipated. If its particles interacted more strongly with normal matter in the early universe, they could have funneled gas into ultra-dense pockets, turbocharging star formation. Another theory suggests these galaxies might be filled with population 3 stars, those primordial behemoths hundreds of times more massive than our sun, burning ferociously and dying young in a spectacle of cosmic fireworks. But even that doesn't fully account for their staggering brightness. Then there's the unsettling possibility that we've misjudged time itself. What if the universe's clock ticked differently in those first epochs? Some speculative models propose that gravity might have been stronger in the early universe, collapsing gas clouds into stars at breakneck speeds. Others wonder if these galaxies are optical illusions lensed or magnified by intervening dark matter we can't see. The implications ripple far beyond a few unusually bright galaxies. If our timeline of cosmic evolution is off by even a few million years, it calls into question everything from the formation of supermassive black holes to the very nature of dark matter. Each observation from Webb adds fuel to the fire, revealing galaxies that look more mature than their age should allow. It's as if the universe handed us a photo album where the baby pictures show full-grown adults, and no one can figure out how they skipped childhood. The longer we stare at these cosmic toddlers bench pressing their way through the early universe, the clearer it becomes. We're missing something fundamental about how galaxies are born. Whether it's a flaw in our models, a hidden force at work, or an entirely new chapter in physics, one thing's certain: the cosmic dawn was far wilder than we ever dared to dream. Deep in the hearts of those impossibly bright early galaxies lurks an even greater enigma: black holes so massive they defy logic. These aren't just your average stellar mass black holes. We're talking behemoths weighing billions of times the mass of our Sun, and they appeared shockingly fast. By the time the universe hit its 1 billionth birthday, these monsters were already fully formed, feasting on matter and powering quasars bright enough to outshine entire galaxies. But here's the cosmic riddle: how did they get so big so quickly? The math simply doesn't add up. Take a typical black hole born from a dying star. It might start with 20 or 30 solar masses. Even if it gorged on gas non-stop, growing at the maximum theoretical rate, it would take far longer than 1 billion years to reach supermassive status. Yet the evidence is written across the early universe in quasars' piercing light. Something had to supercharge their growth, and astronomers are locked in a heated debate over two competing theories, each with staggering implications. First, there's the direct collapse model, a cosmic shortcut so extreme it sounds like science fiction. Picture a primordial gas cloud, pristine and heavy element-free, collapsing under its own weight. But instead of fragmenting into stars, it implodes directly into a black hole with tens of thousands of solar masses in one catastrophic plunge. No supernova, no intermediate steps, just raw gravitational collapse on an unprecedented scale. The conditions for this would have been incredibly rare: gas clouds with just the right density, spinning at just the right speed, bathed in just the right amount of radiation to prevent star formation. Yet if it happened even a handful of times, it could seed the universe with black holes ready to grow into giants. Then there's the stellar remnant camp, which argues even these direct collapse seeds weren't enough. They point to freakishly efficient feeding mechanisms like galaxy-scale gas streams funneling matter directly into black holes at rates that defy our current physics. Imagine a fire hose blasting water into a drain. Now replace the water with entire stars and the drain with a singularity. Some simulations suggest early black holes could have grown exponentially by feasting on dense molecular clouds or even entire star clusters in single apocalyptic meals. But the plot thickens further. Recent observations from the James Webb Space Telescope have spotted supermassive black holes not just in large galaxies, but lurking in tiny, unassuming once black holes that seem disproportionately massive for their galactic homes. This overweight phenomenon suggests their growth might not have depended on their host galaxies at all, upending the long-held belief that black holes and galaxies evolved in lockstep. The stakes of this mystery stretch far beyond black holes themselves. These cosmic vacuum cleaners shaped their surroundings with ferocious energy, heating intergalactic gas and potentially stunting star formation for eons. Their radiation might have been the driving force behind the Epoch of Reionization, peeling back the universe's hydrogen fog. If we misunderstand their origins, we could be misreading the entire timeline of cosmic structure. And then there's the wild card. What if some of these early supermassive black holes weren't born from gas or stars at all? Hypothetical, primordial black holes, forged in the seething chaos of the Big Bang itself, could have been lurking in the darkness long before the first stars flickered to life. Though speculative, their existence would rewrite not just black hole history, but our understanding of the universe's very first moments. Every new observation only deepens the puzzle. Whether through cosmic loopholes, violent feeding frenzies, or physics we've yet to imagine, one thing's clear: the early universe didn't play by the rules we know today. And until we crack this code, the true architects of the cosmic dawn, those shadowy giants pulling strings from the void, will keep their secrets locked away. Stretching across billions of light years like cosmic fingerprints, the Lyman Alpha Forest should be a predictable record of the universe's adolescence. a neat spectrum of hydrogen gas absorption lines imprinted on distant quasar light. Instead, astronomers are staring at chaos. These ghostly patterns, formed as light filters through intergalactic hydrogen clouds, reveal clumps and voids where none should exist, challenging our most fundamental assumptions about how matter distributed itself in the early cosmos. Picture a quasar, a brilliant beacon powered by a supermassive black hole shining through the cosmic dark ages. As its light journeys toward us, it passes through clouds of neutral hydrogen, each one absorbing a specific ultraviolet wavelength called Lyman alpha. The result, a forest of absorption lines in the quasar's spectrum, each dip marking a hydrogen cloud at a different distance. In theory, these lines should follow a smooth distribution, reflecting the universe's gradual clumping under gravity. But the data tells a wilder story. Some regions show hydrogen packed together in dense knots far earlier than models predict, while other stretches appear suspiciously empty, as if something had carved voids into the cosmic web before large-scale structure even formed. One leading suspect is temperature. For decades, simulations assumed the early universe's hydrogen gas cooled uniformly after the Big Bang. But new observations suggest patches remained mysteriously hot, resisting collapse into galaxies. Could leftover heat from the first stars or even decaying dark matter particles have kept these regions from condensing? Alternatively, perhaps the gas was stirred by shock waves from supernova or quasar jets' cosmic turbulence scribbling unexpected patterns into the Lyman alpha record. Then there's the puzzle of coherence. Some gas clouds stretch across millions of light years, their atoms moving in eerie synchrony like a school of fish. Gravity alone can't explain such coordination over these vast scales. Theorists scramble to invoke exotic physics, dark matter interactions weaving unseen filaments, or primordial magnetic fields sculpting gas into aligned structures. Others propose these anomalies are relics of the universe's birth, imprints from quantum fluctuations stretched to cosmic proportions during inflation. The James Webb Space Telescope adds another layer of intrigue. By analyzing the forest's finer details, researchers spotted heavy elements like carbon mingling with pristine hydrogen in clouds that should have been chemically untouched. This contamination hints at far earlier star formation than we'd imagined, with supernova winds polluting intergalactic space before theorists believed possible. What makes these anomalies so critical is their silent testimony. The Lyman alpha forest isn't just a cosmic curiosity, it's a fossilized snapshot of the universe's structure at a pivotal age. If we've misread its patterns, we may be misreading the entire timeline of galaxy formation and the role of dark matter. Each anomalous line whispers secrets about forces we've yet to name, hiding clues to physics beyond our textbooks. As telescopes probe deeper into this spectral forest, one thing becomes clear. The early universe didn't arrange its hydrogen by the rules we wrote. The cosmic microwave background is often called the universe's baby picture, a snapshot of the cosmos at just 380,000 years old, glowing faintly in every direction with the afterimage of the Big Bang. But look closer, and those seemingly uniform waves of heat reveal hidden wrinkles, tiny temperature differences etched into space like cosmic braille. These fluctuations aren't just random noise, they're encrypted messages from the cosmic dawn, holding clues about how energy first flooded the darkness. At first glance, the CMB's temperature variations seem almost mundane, differing by mere millionths of a degree, yet these minuscule ripples tell an explosive story. The hotter spots mark regions where matter was slightly denser, seeds that would eventually grow into galaxies and clusters, thanks to gravity's relentless pull. The cooler patches, those were the cosmic deserts, voids where less gas meant less heat. But buried in this pattern are anomalies that don't fit the standard model. Some cold spots stretch larger than physics should allow, as if vast bubbles of energy were siphoned away long before stars ignited. Others show strange alignments, axis of evil, some jokingly call them where fluctuations seem to whisper about preferred directions in a universe that's supposed to be fundamentally random. Then there's the smoking gun, an elusive signal known as the cosmic infrared background. This faint glow superimposed on the CMB comes from the cumulative light of all the first stars and galaxies. But here's the puzzle: it's brighter than expected, way brighter. Either the cosmic dawn burned twice as fiercely as we thought, or something else, perhaps dark matter decay or primordial black holes, was pumping extra energy into the early universe. The CMB holds traces of that energy, imprinted as subtle distortions in its polarization patterns. Most tantalizing of all is the shadow of reionization. As ultraviolet light from the first stars ripped electrons from hydrogen atoms, it left a unique fingerprint on the CMB's polarization, a swirling pattern that should, in theory, reveal exactly when and how the cosmic fog lifted. But the data tells a messier story. Some measurements suggest reionization happened in fits and starts, with bubbles of clarity popping up earlier than expected, while other regions clung stubbornly to their hydrogen haze. The Planck satellite's painstaking maps hint that this process may have begun shockingly early, perhaps even before the universe's 500 millionth birthday, throwing our entire timeline of cosmic evolution into question. What makes these CMB riddles so critical is their reach. Unlike fossils buried in rock, these microwave whispers haven't faded over billions of years. They've traveled uninterrupted since the dawn of time, carrying unfiltered truth about the universe's rawest moments. Every anomaly, every deviation from expectation isn't just a curiosity, it's a potential crack in our understanding of physics itself. Whether it's evidence of parallel universes brushing against ours, relics of cosmic strings from the Big Bang, or simply a sign that dark energy behaves differently than we thought, one thing is clear: the CMB isn't just a relic of the past. It's a treasure map pointing towards secrets we've only begun to uncover. The early universe was supposed to be a time of purity, vast oceans of hydrogen and helium untouched by heavier elements, relics of the Big Bang itself. These pristine gas clouds, free from the pollution of metals forged in stars, should still drift through space today like cosmic time capsules. Yet when astronomers scour the cosmos for these primordial pockets, they come up nearly empty-handed. It's as if someone scrubbed the universe clean before we could take inventory, a mystery dubbed the missing metal-free gas that hints at forces reshaping the cosmos in ways we never anticipated. The search for these untouched clouds isn't just academic. They're the last witnesses to a universe before starlight, holding clues about conditions during the cosmic dawn. Theory suggests they should exist especially in the voids between galaxies where star formation never took hold, but observations tell a different story. Even the most remote gas clouds show traces of heavier elements like carbon and oxygen, elements that only form in the hearts of stars or the fury of supernova. So how did these metals spread so far, so fast, infiltrating even the deepest cosmic backwaters? One explanation points to the fury of those first stars. Their supernova weren't just explosions, they were cosmic pressure washers, blasting metals across millions of light years at speeds approaching 10% the speed of light. Simulations show these shockwaves could have enriched even distant gas clouds within a few 100 million years, turning pristine hydrogen into contaminated soup. But there's a problem: some regions are too polluted. The metal concentrations are higher than even the most violent supernova should produce, suggesting something else, something bigger, was at work. Enter quasars, the universe's ultimate polluters. These supermassive black holes, devouring matter and spewing jets of radiation, could have acted like cosmic sprinklers, spraying heavy elements far beyond their host galaxies. Their winds travel fast enough to reach intergalactic space in relatively short order, painting the cosmos with metals long before smaller stars had a chance to contribute. Yet even this doesn't solve the entire puzzle. Recent observations reveal metal-free gas isn't just rare, it's practically non-existent. The few candidates that do appear pristine often turn out to have faint metal signatures upon closer inspection. This absence suggests an even earlier wave of pollution, perhaps from population Roman III stars that lived and died before most galaxies even formed. Some theorists speculate these stars might have dispersed metals in ways we don't yet understand, through exotic supernova or even dark matter interactions. The implications ripple far beyond a few missing gas clouds. If metals spread faster and farther than our models predict, it reshapes how we understand everything from galaxy formation to the chemistry of life itself. Heavy elements are the building blocks of planets and life. Their premature dispersal might mean planets and possibly life had a head start we never accounted for. But what if the answer isn't about pollution at all? A radical alternative suggests these primordial clouds do exist, they're just hiding in plain sight. If the gas is too diffuse or too hot, it might not absorb light in ways our telescopes can detect. Or perhaps magnetic fields or dark matter interactions have altered its behavior, making it invisible to conventional surveys. The mystery of the missing metal-free gas isn't just about what's absent, it's about forces we've yet to imagine. Processes that sculpted the universe in its infancy with an efficiency we're only beginning to grasp. Every empty patch of sky whispers about a cosmic dawn far more dynamic and far messier than we ever dreamed. In the quiet static between galaxies, a mysterious whisper from the cosmic dawn has astronomers scratching their heads. Back in 2018, a humble ground-based radio telescope called EDGES picked up something extraordinary, a 21-centimeter absorption signal dating back to just 180 million years after the Big Bang. That in itself would have been groundbreaking, but what really sent shockwaves through cosmology was the signal's staggering strength. It wasn't just a faint ripple in the cosmic background, it was twice as deep as anyone predicted, plunging like an unexpected trench in the smooth terrain of early universe physics. This anomaly isn't just a technical blip, it's a potential window into forces we've never seen. The 21-centimeter signal comes from hydrogen atoms absorbing photons at a specific wavelength, triggered by the first starlight bathing the cosmos. But for the dip to be that pronounced, something had to cool the hydrogen gas way more than our models account for. Enter the wild theories. One leading idea suggests dark matter, normally aloof and indifferent to ordinary matter, might have played an unexpected hands-on role in the early universe. If certain dark matter particles interacted with hydrogen, transferring energy like cosmic refrigerants, they could have chilled the gas to temperatures we can't explain otherwise. Then there's the radiation angle. The signal's depth also depends on how intense the first starlight was. If early stars or black holes pumped out far more ultraviolet radiation than we thought, that could amplify the absorption. But here's the catch. No known astrophysical objects match the required specs. Some speculate exotic phenomena, like annihilating dark matter or primordial black holes evaporating in bursts of energy, might have flooded the universe with extra radiation. Others wonder if our assumptions about the cosmic microwave background's temperature at that epoch are fundamentally off. The implications spiral outward. If dark matter did interact with hydrogen, even briefly, it rewrites the rulebook for how structure formed in the universe. Suddenly, this elusive substance isn't just a passive scaffold, it's an active participant, shaping the cosmos in ways we never anticipated. Alternative models like dark photons or Miller-charged particles suddenly come into play, suggesting a shadowy subatomic world humming beneath the surface of ordinary physics. But not everyone's convinced the signal is real. Ground-based observations are notoriously tricky, vulnerable to interference from Earth's atmosphere or even radio pollution from human technology. Competing teams have scrambled to confirm the finding with mixed results. The difficulty lies in separating this ancient whisper from the cacophony of modern radio noise, like trying to hear a pin drop in a hurricane. Upcoming space-based missions, like the proposed lunar surface electromagnetics experiment, aim to sidestep these issues by placing detectors on the far side of the moon where Earth's chatter falls silent. What makes this mystery so tantalizing is its duality. The signal could be a fluke, an artifact of unaccounted-for noise, or it could be the first tangible clue that dark matter isn't as dark as we thought. Either way, the universe seems to be hinting at hidden chapters in its origin story, waiting for us to decode the whispers trapped in the static. Among the most baffling discoveries from the cosmic dawn is this: quasars separated by distances so vast they could never have communicated billions of light-years apart, somehow pointed their jets in the same direction. It's as if an invisible cosmic hand lined them up like compass needles, defying every expectation that the universe should be random, chaotic, and isotropic. These aren't just isolated cases. Studies of hundreds of early quasars reveal alignment on scales that dwarf entire galaxy clusters, hinting at forces or structures we've yet to comprehend. The jets themselves are already cosmic oddities, twin beams of plasma screaming from the poles of supermassive black holes at nearly light speed, stretching millions of light-years into space. They're the universe's most powerful particle accelerators, capable of shaping entire galaxies, but their alignment is the real puzzle. If black holes spin randomly, as theory suggests, their jets should spray in all directions like a garden sprinkler. Instead, they're coordinated, as if dancing to some hidden rhythm. One explanation points to the influence of the cosmic web, the vast filamentary network of dark matter and gas weaving through the universe. These filaments, stretching across incomprehensible distances, might act like cosmic highways, channeling gas onto black holes in a uniform way. As the black holes feed, their spin axes align with the flow, much like a spinning top orients itself along the direction it's pulled. Simulations show this could create regional coherence, where quasars in the same filament point similarly, but the observed alignments span multiple filaments, crossing voids where no such gas flows exist. The scale is simply too grand for this alone to explain. Then there's the magnetism angle. Some theorists propose primordial magnetic fields woven into the fabric of space-time during the Big Bang could have gently steered these jets into alignment over billions of years. Imagine invisible threads tugging at every black hole, guiding their spin like puppets on strings. The problem: we've never detected magnetic fields strong or organized enough on such scales. And if they exist, they'd imply physics beyond our current model's forces that operated in the early universe with precision we can't replicate. Perhaps the most radical idea involves the universe's very structure. What if the Big Bang didn't leave space perfectly uniform? Tiny rotational twists imprinted in the early cosmos, a phenomenon called cosmic vorticity, might have set a preferred direction for everything that followed, from galaxy rotation to black hole spins. It's speculative, but not impossible. After all, the cosmic microwave background already shows puzzling large-scale anomalies that hint at a universe slightly lopsided in ways we don't yet understand. What makes this mystery so profound is its implications. If randomness isn't the rule, if some hidden order governed the cosmic dawn, it challenges our deepest assumptions about how structure emerged. Maybe dark matter played a role we've missed, or perhaps black holes didn't form independently but were birthed along some unseen scaffold, their spins locked from the beginning. Every quasar pointing in unison is a silent protest against the chaos we thought defined the universe, urging us to look deeper into the darkness for answers. Among the first flickers of light in the cosmic dawn, there might have been stars unlike anything we've ever imagined, and not powered by nuclear fusion in their cores, but by something far stranger, the annihilation of dark matter itself. These hypothetical beasts, dubbed dark stars, could rewrite the story of how the universe lit up after the Big Bang. And with the James Webb Space Telescope finally peering into that ancient epoch, we might be on the verge of proving they were real. Picture a star, but strip away everything familiar. Instead of crushing hydrogen into helium under unimaginable pressure, its core hums with the eerie glow of dark matter particles colliding and obliterating one another, releasing energy in a slow, steady burn. These wouldn't be fleeting objects without the frantic pace of fusion. Dark stars could grow to monstrous proportions, ballooning to millions of times the mass of our Sun and shining with the brightness of entire galaxies. Yet their light would be different, cooler and redder than fusion-powered stars, like cosmic embers rather than blowtorches. The idea hinges on dark matter being more than just a gravitational ghost. If certain types of weakly interacting massive particles WIMP exist, they could accumulate in the cores of early protostars, drawn in by gravity and then trapped, colliding and annihilating in a self-sustaining feedback loop. The energy output would be just enough to prevent the star from collapsing further and igniting conventional fusion, creating a bizarre hybrid, a star fueled by shadows. Critics argue the hypothesis stretches plausibility. For dark stars to form, the early universe would have needed dense clumps of dark matter exactly where the first gas clouds coalesced, a fine-tuned scenario. Plus, we've never directly detected WIMP despite decades of searching. But supporters counter that the cosmic dawn was a unique environment, with dark matter distributed far more densely than today. In those extreme conditions, even rare interactions could have dramatic effects. Now, the James Webb Space Telescope is hunting for the telltale signatures of these phantom beasts. Dark stars would leave distinct fingerprints in infrared light, spectral lines hinting at their unusual energy source. Some scientists are even re-examining Webb's images of extremely early, inexplicably bright galaxies, asking, could these actually be clusters of dark stars masquerading as ordinary galaxies? The key lies in their temperature and composition. True dark stars would lack heavy elements entirely, their light unpolluted by the metals forged in later supernova. If confirmed, the implications would ripple across cosmology. Dark stars could explain how supermassive black holes grew so quickly, their massive cores collapsing directly into black holes without the messy supernova stage. They might even account for some of the missing light in the cosmic dawn, their steady glow filling gaps in the timeline of reionization. But the biggest revelation would be about dark matter itself, proof that it's not just an invisible scaffold, but an active player in cosmic evolution, shaping the universe's first light in ways we're only beginning to grasp. Every unexplained dot in Webb's deep field images could be a dark star waiting to be unmasked. And if we find even one, it won't just solve a mystery, it'll open a door to a hidden chapter of physics, written in the slow burning fire of the universe's shadowy dawn. The early universe wasn't just assembling stars and galaxies, it was undergoing a covert chemical revolution. Within mere hundreds of millions of years, the cosmos went from sterile simplicity, hydrogen, helium, and not much else, to a surprisingly rich soup of heavier elements, carbon, oxygen, iron, even gold. But here's the head-scratcher. These metals didn't just linger near their stellar birthplaces. They flooded intergalactic space at breakneck speeds, contaminating even the most remote gas clouds far from any known galaxy. This rapid pollution hints at stellar processes far more violent and efficient than anything we see today, a cosmic gold rush where elements spread like wildfire. Take supernova, the universe's elemental forges. When massive stars die, they explode with enough force to blast their chemically enriched guts across light years. But in today's universe, that material typically stays localized, gradually mixing with surrounding gas over eons. The early cosmos played by different rules. Some primordial supernova might have been hypernova, explosions 10 to 100 times more energetic than standard stellar deaths, their shockwaves punching through galactic boundaries. Others could have been pair instability supernova, a rare breed of detonation where stars so massive, we're talking 200 solar masses or more, become unstable and annihilate themselves completely, leaving no black hole behind, just an expanding shell of heavy elements traveling at incredible speeds. Yet even these stellar catastrophes might not explain the full picture. Observations of distant quasars reveal metal-rich gas clouds so far from galaxies that conventional supernova winds would have taken billions of years to reach them, not the few 100 million years the cosmic timeline allows. This suggests another, even more extreme dispersal mechanism: black hole jets. Supermassive black holes in the early universe didn't just sit quietly. They gorged on surrounding matter, belching out plasma jets at near light speeds. These jets could have acted like interstellar fire hoses, spraying metals across vast cosmic distances in geological instants. But the plot thickens when we examine the metal ratios themselves. Some ancient gas clouds show bizarrely high concentrations of elements like carbon and oxygen relative to iron, a chemical signature that doesn't match any known supernova type. This anomaly has led theorists to propose entirely new classes of stellar objects that might have existed only in the cosmic dawn. One candidate: supermassive stars powered by dark matter annihilation, whose unique nuclear burning could produce exotic elemental mixes. Another: rapidly spinning collapsars, whose violent deaths unleashed narrow, ultra-fast jets specifically enriched in certain elements. Then there's the wild card of population Roman 3 stars themselves. These first-generation behemoths may have shed material in ways modern stars can't, through colossal stellar winds or pulsational eruptions, pre-polluting their surroundings before they even exploded. Some models suggest their supernova could have been cold, producing unusually large amounts of dust that then rode radiation pressure to distant corners of the cosmos. What makes this mystery so pivotal is its connection to life itself. Heavy elements are the building blocks of planets and biology. If metals spread faster and farther than we thought, it means the raw ingredients for life had a head start, potentially making habitable worlds possible earlier in cosmic history than anyone guessed. Every unexpectedly metal-rich cloud we find is a challenge to rewrite the story of how and when the universe became chemically ready for us. The speed of this enrichment doesn't just defy expectations, it hints at a lost era of stellar and galactic behavior far more frenetic and fertile than anything we see today. The cosmic web should have been one of the first large-scale structures to emerge from the chaos of the early universe, a sprawling network of filaments connecting galaxies like threads in a vast, invisible tapestry. According to our most sophisticated simulations, these tendrils of dark matter and gas should have taken shape within the first few billion years, knitting the universe together under gravity's relentless pull. But when astronomers began mapping the actual cosmic web using quasars as backlights, they stumbled upon a glaring discrepancy. The web was late by at least 1 billion years. This isn't just a minor timing issue. It's a fundamental challenge to our understanding of how gravity shapes the cosmos. Imagine pouring syrup onto a plate and watching it slowly spread into delicate strands. That's essentially how cosmologists thought the cosmic web formed, with dark matter's gravity drawing gas into filamentary rivers over time. But the real universe seems to have dragged its feet. Recent observations reveal vast regions where filaments are thinner, sparser, or even missing altogether at epochs when they should have been fully established. It's as if cosmic infrastructure crews showed up late to the job, leaving entire sections of the universe uncabled. So what stalled the process? One possibility flips the script on dark matter itself. Maybe it wasn't as cold as we assumed. The standard model treats dark matter particles as slow-moving, hence cold, allowing them to clump easily. But if some dark matter was slightly warmer, with particles zipping around faster, they'd resist clustering into fine filaments early on. Think of trying to weave a net with marbles versus ping-pong balls. The latter would scatter too easily to form tight connections. This lukewarm, dark matter scenario could explain the lag, though it would require tweaking decades of cosmological orthodoxy. Then there's the wild card of cosmic feedback. Those first galaxies and quasars didn't just form passively, they fought back. Supernova and black hole jets blasted surrounding gas with enough energy to counteract gravity's pull, potentially delaying filament formation in certain regions. Simulations that include these violent feedback effects show patchy, delayed webs resembling observations far better than pristine models. But here's the catch. The scale of this disruption would require feedback mechanisms far more efficient than anything we see in the modern universe, as if early stars and black holes operated with some sort of forgotten cosmic overdrive. The most unsettling explanation challenges gravity itself. What if Einstein's theory, while brilliantly accurate on smaller scales, needs adjustment when applied to the vast, diffuse structures of the early cosmic web? Modified gravity theories like MND have long proposed tweaks to explain galactic rotation without dark matter. Now, some theorists suggest similar adjustments might account for the web's tardiness, with gravity weakening just enough over megaparsec distances to slow filament growth. The James Webb Space Telescope is now hunting for these missing filaments by tracing the faint glow of hydrogen atoms within them. Preliminary data reveals some strands are indeed fainter than expected, while others appear twisted or fragmented, clues that the early web was a far messier construction site than we envisioned. Every new observation peels back another layer of this mystery, forcing us to confront an uncomfortable truth. Either dark matter behaves in ways we've never seen, or gravity's rules aren't as universal as we thought. The cosmic web's delay isn't just a footnote in cosmology, it's a blinking neon sign pointing toward physics we've yet to discover. Hidden in the void between the bright pinpoints of known galaxies might lie ghosts, entire islands of stars so dim they've slipped through every observational net. These phantom galaxies, dominated by dark matter with only the faintest whisper of visible matter, could be the key to solving one of cosmology's most persistent puzzles, the missing baryon problem. We know ordinary matter, the stuff that makes up stars, planets, and us, should account for about 5% of the universe's mass. But when we tally up all the glowing gas and galaxies we can see, nearly half of it's unaccounted for. Enter Galaxy X, the catch-all name for these elusive dark galaxies that may be hoarding the universe's lost atoms in their shadowy embrace. The hunt for these cosmic wraiths isn't just about filling a ledger, it's a test of our fundamental understanding of structure formation. Dark matter's gravity should have pulled ordinary matter into countless small galaxies, many of which would be too dim to form stars efficiently. Yet when we scan the skies with even our most powerful telescopes, these predicted legions of faint galaxies remain conspicuously absent. Some theorists argue we've been looking for them all wrong, that their starlight is so feeble, it's drowned out by the glare of nearby objects or lost in the infrared haze of interstellar dust. Others suspect their stars might be spread so thin that the galaxies blend into the background like ink diluted in an ocean. But there's tantalizing evidence these ghosts are real. Take the bizarre case of Dragonfly 44, a galaxy in the nearby Coma cluster. It weighs as much as the Milky Way but emits less than 1% of its light, a celestial heavyweight with the glow of a candle. Then there's Antlia 2, a dwarf galaxy orbiting the Milky Way so diffuse that stars slip through its grip like grains of sand. These oddballs might be the tip of the iceberg, hinting at a hidden population of ultra-diffuse galaxies lurking in the darkness. The real breakthrough could come from gravitational lensing, nature's magnifying glass. When dark matter clumps bend light from distant objects, they reveal their presence without emitting a single photon. Already, astronomers have spotted telltale distortions in background galaxies that can't be explained by known matter, suggesting invisible galaxies are warping space-time around them. The challenge, pinpointing their exact locations and masses, requires painstaking analysis of statistical anomalies in vast datasets, like finding footsteps in snow that's already melting. If these dark galaxies do exist, they might solve more than just the missing baryon problem. Their sheer abundance could explain why the cosmic web seems to have formed later than predicted. Their gravity might have subtly slowed the growth of filaments. Their star-forming inefficiency could also account for why some regions of the early universe reionized faster than others. With so many galaxies failing to ignite, ultraviolet light might have leaked unevenly across the cosmos. The search for Galaxy X isn't just about finding invisible islands, it's about confronting the possibility that our cosmic maps are missing whole continents. Every unexplained lensing signal, every gap in the baryon budget, whispers that we're surrounded by ghosts. And if we can learn to see in the dark, we might finally understand how much of the universe we've been missing all along. The cosmic fog didn't lift all at once. It peeled back in ragged, uneven patches like morning mist burning off a lake in unpredictable swirls. This patchwork of light and shadow across the early universe, known as reionization bubbles, defies every expectation of how illumination should have spread during the cosmic dawn. If the first starlight truly flooded the cosmos like a sunrise, why do we see jagged islands of clarity mixed with stubborn pockets of lingering darkness hundreds of millions of years later? This cosmic jigsaw puzzle holds vital clues about the forces that shaped our universe's transparency, and the answers might rewrite everything we know about the power of those first stars and galaxies. For decades, the Standard Model painted reionization as a relatively uniform process. Ultraviolet radiation from early galaxies and quasars would have slowly ionized surrounding hydrogen gas, creating expanding bubbles of clarity that eventually overlap to reveal the universe we see today, a bit like ice melting across a pond's surface. But observations from the Hubble and now the James Webb Space Telescope reveal a messier reality. Some regions appear fully ionized astonishingly early, while others cling to their neutral hydrogen for far longer than physics predicts. The most striking example comes from quasars spotted just 800 million years after the Big Bang. Their light shows alternating bands of ionized and neutral gas along the line of sight, clear evidence that reionization was a chaotic patchwork, not a smooth wave. One leading theory suggests the culprit might be the very nature of those first galaxies. Unlike modern galaxies with orderly spiral arms, early star systems were small, irregular, and prone to explosive bursts of star formation. When these compact galaxies ignited, their intense UV radiation could have blown enormous bubbles in the surrounding hydrogen fog, but only in their immediate vicinity. Vast stretches of intergalactic space might have remained in shadow, untouched by these localized fireworks. Simulations show this could create a Swiss cheese universe where ionized tunnels carved by galaxy clusters wind through untouched neutral regions like cosmic voids. But there's a twist. Some of these bubbles are too large. Certain ionized regions stretch across hundreds of millions of light years, far bigger than even the most optimistic models of early galaxy influence can explain. This has led to wilder hypotheses, including the possibility of dark stars or other exotic objects supercharging reionization in specific zones. One provocative idea involves decaying dark matter particles releasing bursts of energy that could have ionized hydrogen without any starlight at all. Another points to supermassive black holes acting as cosmic lighthouses, their beams sweeping across the cosmos and carving out vast transparent corridors ahead of schedule. The most perplexing clue comes from the bubble's edges. In some areas, the transition between ionized and neutral gas is razor-sharp, as if something is actively containing the expansion of light. This shouldn't happen. Ionization fronts should blur as they propagate. One explanation invokes dense filaments of the cosmic web acting like firebreaks, their tangled hydrogen strands resisting ionization longer than diffuse regions. Alternatively, there might have been a previously unknown feedback mechanism at work, perhaps early magnetic fields or even radiation pressure from stars creating temporary barriers. These bubbles aren't just cosmic curiosities, they're forensic evidence. Their sizes, shapes, and distributions encode secrets about how the first structures formed and interacted. If quasars dominated reionization, bubbles should be large and centered around bright points. If dwarf galaxies did most of the work, we'd expect smaller, more numerous bubbles. Current data fits neither pattern neatly, suggesting a complex interplay of forces we're only beginning to untangle. The James Webb Space Telescope is now mapping these bubbles in 3D by analyzing thousands of quasar spectra, building a tomographic image of the early universe's evolving transparency. What emerges is a story of cosmic inequality, a universe where light didn't spread democratically, but surged through some regions while barely touching others. This uneven dawn might explain why some galaxies formed earlier than others, why certain black holes grew to monstrous sizes so quickly, and even why the cosmic web shows unexpected voids in its structure. The reionization bubbles aren't just remnants, they're the fingerprints of a struggle between light and darkness that shaped everything that followed, a battle whose rules we're still deciphering. At the very edge of our cosmic timeline, where the first galaxies were supposed to be taking their tentative first steps, astronomers have stumbled upon something that shouldn't exist: teenage galaxies already throwing a raucous house party. These aren't just isolated early galaxies, they're massive, fully formed clusters packed together in dense neighborhoods billions of years before our models say they should have gathered. It's like finding a bustling metropolis in what was supposed to be the Stone Age of the universe, and it's forcing us to rethink how structure emerges from chaos. The conventional story of cosmic growth is one of slow accumulation, small things merging over time to form bigger things. Dwarf galaxies collide to form spirals, spirals cluster into groups, and eventually, those groups assemble into the massive city-like galaxy clusters we see today. This hierarchical model has been the backbone of cosmology for decades, beautifully explaining the universe's large-scale structure. But the James Webb Space Telescope has shattered that narrative, spotting fully fledged protoclusters, the seeds of future galaxy megacities already in place when the universe was less than 1 billion years old. Some contain dozens of massive galaxies, crammed into regions just a few million light-years across, their gravitational pull warping spacetime enough to lens background light into eerie arcs. What makes these clusters impossible isn't just their existence, it's their maturity. Their galaxies aren't the small, chaotic blobs we'd expect in the cosmic dawn. They're massive, chemically evolved, and often already bulging with stars. Spectroscopy reveals heavy elements like oxygen and carbon in their atmospheres, elements that should have taken multiple generations of stars to produce. It's as if these galaxies skipped childhood entirely, jumping straight into adolescence while the rest of the universe was still in diapers. The most infamous example is a protocluster dubbed Hyperion, spotted in data from the Very Large Telescope. Stretching across a region of space that should have been relatively empty at that epoch, it's a spiderweb of galaxies interconnected by filaments of gas, already outlining the cosmic web structure in shocking detail. But Hyperion isn't alone. Every deep field image from Webb seems to uncover another of these overachievers, each one more developed than the last. So how did they cheat cosmic evolution? One radical theory suggests dark matter didn't clump as gradually as we thought. If certain types of dark matter particles interacted with each other, colliding or annihilating in ways that released extra energy, they could have jump-started structure formation in localized regions, creating dense hubs where galaxies formed at breakneck speed. Others propose these clusters might have formed in rare, ultra-dense patches left over from the Big Bang itself, cosmic lottery winners born with a head start. But the implications go deeper than just timing. If galaxies could assemble into clusters this early, it means the universe's first large-scale structures might have wielded outsized influence. Their collective gravity could have funneled gas into central black holes at unprecedented rates, explaining how supermassive monsters grew so quickly. Their intense radiation might have carved early ionization bubbles that altered the course of reionization, and their very existence hints that the cosmic web, the universe's underlying structure, might have been sketched in bolder strokes than we ever realized. The true shock isn't just that these protoclusters are breaking the rules, it's that they might be rewriting them entirely. Every new observation peels back another layer of our ignorance, revealing a cosmic dawn far more complex, far more precocious, and far more mysterious than we ever dreamed. Galaxy clusters should be cosmic furnaces, cauldrons of superheated gas swirling at millions of degrees, their immense gravity squeezing matter until it glows brighter than a billion suns. Yet when astronomers peer into the early universe, they find something utterly baffling. Pockets of gas in these clusters cooling too fast, as if some invisible hand flipped a cosmic thermostat to max. These cooling flows defy every expectation, draining energy from the system at rates that leave theorists scrambling for explanations. What's stealing the heat from these cosmic cauldrons? The answer might rewrite our playbook for how galaxies and black holes conspire to shape their surroundings. At the heart of the mystery lies a paradox. The gas in galaxy clusters is so hot it emits X-rays, and over billions of years, it should gradually lose energy and cool, but not this quickly. Simulations predict cooling rates 100 times slower than what we observe in some ancient clusters. It's like expecting a cup of coffee to stay warm for hours, only to watch it frost over in minutes. Something is turbocharging the cooling process, and the prime suspect is hiding in plain sight. Supermassive black holes at the cluster's cores. We've long known these black holes aren't passive monsters. As they devour matter, they spew jets of plasma and radiation powerful enough to heat surrounding gas, creating a balancing act that prevents runaway cooling. But in the early universe, this feedback loop seems to have worked in reverse. Instead of pumping heat into the system, some black holes might have triggered bizarre, cooling storms by stirring the gas in just the right way. Picture a spoon swirling cream into coffee. The motion itself doesn't heat or cool the liquid, but it changes how heat distributes. Similarly, black hole jets could have churned cluster gas into turbulent eddies, accelerating heat loss through chaotic mixing. Then there's the dark matter wild card. If certain dark matter particles interact weakly with the hot gas transferring energy without emitting light, they could act like stealthy refrigerants, silently siphoning heat away. This would leave no trace in visible or X-ray observations, only revealing itself through the gas's inexplicable chill. Some theorists even speculate about primordial magnetic fields, woven into the cluster's fabric during the Big Bang, that might guide heat along invisible pathways out of the system. The smoking gun, strange filaments of cold gas spotted winding through these clusters like icy veins in a scorching body. These tendrils shouldn't exist. Hot gas should suppress their formation, yet there they are, threading through the chaos. Their presence suggests cooling isn't just happening. It's happening in concentrated, organized channels, as if the cluster has a hidden circulatory system. The implications ripple far beyond astrophysics. If cooling flows are more efficient than we thought, early galaxies could have formed stars at breakneck speeds, explaining why some appear overly mature in the cosmic dawn. It might also solve the puzzle of how supermassive black holes grew so quickly. They'd have had a steady buffet of cold gas funneled straight to their cores. But the real lesson is humbling. Even the most violent places in the universe obey laws we're still deciphering. Every anomaly in those ancient clusters whispers about forces we've yet to name, hidden in the delicate dance between heat, gravity, and shadow. Black holes come in two flavors we know well: the small, stellar mass leftovers of dead stars, and the supermassive beasts anchoring galaxy centers. But where's the middle child? The cosmic family photo has a glaring gap: intermediate black holes, those missing links weighing between 100 and 100,000 solar masses. Their absence isn't just a curiosity, it's a glaring hole in our understanding of how cosmic monsters grow. Think of black hole evolution like a ladder. At the bottom rung, you've got stellar remnants, black holes formed when massive stars collapse, typically weighing between 5 and a few dozen solar masses. At the top, supermassive black holes loom billions of times heavier than our Sun, squatting in galactic cores like insatiable kings. Logic says there should be steps between them, black holes that started small and merged or feasted their way up the weight classes. Yet despite decades of searching, these middleweights remain elusive. We've found a handful of candidates, but nothing like the swarms our models predict. One prime hunting ground should be globular clusters, dense balls of ancient stars where black holes could easily meet, merge, and grow. Simulations show that in these crowded environments, stellar mass black holes should sink to the center over time, colliding and forming intermediates. But when astronomers peer into these clusters, the expected beasts rarely appear. The few candidates we do spot, like the potential 400 solar mass black hole in the Andromeda Galaxies cluster B023, are exceptions that prove the rule. Each discovery feels like finding a needle in a cosmic haystack. Their absence throws a wrench into our theories of supermassive black hole origins. If these giants grew from repeated mergers of smaller black holes, where are all the intermediate steps? One possibility is that they're hiding in plain sight, disguised as something else. Some ultraluminous X-ray sources, mysterious objects pouring out insane amounts of energy, might actually be intermediate black holes in disguise, their true masses obscured by their frenzied feeding. Others could be lurking in dwarf galaxies, their modest surroundings making them harder to spot than their supermassive cousins in brighter galaxies. Then there's the dark horse theory. Maybe intermediate black holes are rare because they don't stick around long. If they form in dense environments, they might quickly merge or get kicked out of their host clusters by gravitational interactions before we can spot them. Picture a cosmic game of pinball where black holes get slingshot into intergalactic space before they can grow. Alternatively, perhaps the early universe had a shortcut, some mechanism that let black holes skip the intermediate phase entirely, jumping straight from stellar mass to supermassive in one dramatic leap. The implications ripple far beyond classification. If intermediate black holes truly are missing, it might mean supermassive black holes didn't grow gradually, they were born big. Some models suggest direct collapse from giant primordial gas clouds could have birthed black holes tens of thousands of times the Sun's mass right out of the gate. Others propose exotic physics like dark matter interactions or quantum effects that could have accelerated their growth beyond what standard mergers allow. Every null result, every empty search tightens the mystery. The missing intermediates aren't just a gap in our catalogs, they're a silent challenge to our theories of cosmic evolution. Until we find them, or conclusively prove they don't exist, we're left with an unsettling truth. Somewhere between the smallest black holes and the largest, the universe is playing by rules we haven't yet decoded. Among the most enigmatic signals ever detected from deep space, fast radio bursts pack more energy in a millisecond than our Sun emits in 3 days, yet their origins remain one of astronomy's fiercest puzzles. While most of these fleeting cosmic flashes seem to hail from relatively recent epochs, a handful exhibit characteristics hinting they might be relics from the cosmic dawn. If confirmed, these ancient radio bursts could serve as probing beacons, illuminating conditions in the early universe that no telescope can directly see. Take one peculiar burst catalogued as FRB 20180916b. Unlike typical fast radio bursts, its signal carried an unusual fingerprint, a telltale smear of dispersed radio waves suggesting it traversed an extraordinary amount of ionized gas before reaching us. When researchers backtracked its path, they calculated this burst likely originated when the universe was less than 2 billion years old, placing it squarely in the era when the first galaxies were ionizing their surroundings. The real shock came when they analyzed its polarization, the way its radio waves were twisted. This burst light bore the distinct spiral signature of having passed through an intensely magnetized environment, far stronger than anything seen in the modern cosmos. This raises a tantalizing possibility. Could fast radio bursts be the dying screams of Magnetar's ultra-dense, highly magnetized stellar remnants born from the first generation of stars? Population Roman 3 stars, those primordial behemoths hundreds of times the Sun's mass, would have died violent deaths, some collapsing into magnetars with magnetic fields 1,000 trillion times Earth's. Such an object, vibrating or cracking under its own unimaginable magnetic stress, might release precisely the kind of energy we observe in fast radio bursts. Even more intriguing, these bursts could act as cosmic probes. As their signals slice through intergalactic space, they pick up subtle imprints from the gas and magnetic fields they encounter, like a flashlight beam revealing dust in a dark room. But alternative explanations abound. Some theorists propose that fast radio bursts from the cosmic dawn might originate from cataclysmic collisions, perhaps neutron stars spiraling into black holes in dense primordial star clusters. Others suggest they could be signatures of cosmic strings, hypothetical defects in space-time left over from the Big Bang itself, vibrating like plucked guitar strings. The most radical idea, these bursts might be evidence of primordial black holes evaporating in bursts of Hawking radiation, their death throes echoing across billions of years. What makes these distant bursts so valuable isn't just their power, it's their rarity. The further back we look, the fewer fast radio bursts we detect, suggesting either that their sources were less common in the early universe or that their signals have been diluted beyond recognition by cosmic expansion. Each one we do catch becomes a precious time capsule, encoding information about the magnetic fields and gas distribution during the universe's most formative age. Perhaps the most groundbreaking revelation would be if these bursts trace the cosmic web's magnetic skeleton. Simulations suggest the first magnetic fields emerged from tiny seed fields amplified by the motion of gas along filaments of the cosmic web. Fast radio bursts passing through these regions should bear their imprint, offering an indirect way to map structures we can't otherwise see. Already, tentative evidence suggests some bursts show signs of traversing magnetized filaments like a compass needle twitching in response to some vast, invisible lattice. The search continues with radio telescopes like CHIME and the upcoming Square Kilometre Array poised to catch more of these cosmic messengers. Every new ancient fast radio burst adds another piece to the puzzle, teasing us with the possibility that these fleeting signals might hold the key to understanding how the universe first learned to glow and how magnetism wove itself into the fabric of cosmic history. The early universe wasn't just a simmering cosmic soup, it was a roaring furnace burning hotter than anyone anticipated. Observations of distant gas clouds reveal a startling truth. The intergalactic medium, the vast expanse between galaxies, was scalding just 1 billion years after the Big Bang. Temperatures soared thousands of degrees higher than models predict, as if some unseen force cranked up the heat across the cosmos. This isn't just a minor discrepancy, it's a glaring anomaly that hints at energy injections beyond anything our current physics can explain. The smoking gun comes from quasar light. As these brilliant beacons shine through ancient gas clouds, their spectra bear the fingerprints of heated hydrogen atoms agitated to extremes long before the first galaxies should have had the power to warm their surroundings. The most puzzling part, this heat isn't localized, it's pervasive, stretching across vast cosmic voids where no known sources of energy could have reached. Something or someone left the universe's thermostat turned to max, and we're only now discovering the aftermath. One leading suspect is the first generation of black holes. While quasars are known to blast their surroundings with radiation, their influence alone can't account for the sheer scale of this heating. theories suggest legions of smaller, hidden black holes, stellar remnants from population Roman 3 stars, might have collectively pumped energy into the cosmos like invisible radiators. Their X-ray emissions could have seeped into intergalactic space, reheating gas that had barely cooled since the Big Bang. But even this falls short. Simulations show these black holes would need to be implausibly efficient, converting nearly all their consumed matter into heat to achieve the observed temperatures. Then there's the dark matter wild card. If certain dark matter particles decayed or annihilated in the early universe, they might have unleashed torrents of energy capable of warming the cosmic gas. Some models propose dark photons, hypothetical particles acting as intermediaries between dark and normal matter, could have transferred heat without leaving direct traces. Others speculate about primordial magnetic fields woven into the fabric of space during inflation, whose decay might have sparked colossal heating events. The challenge: we've yet to detect any of these phenomena directly, leaving their existence firmly in the realm of what if. But the plot thickens with the role of cosmic rays. The violent deaths of those first stars, hypernova and collapsars, could have accelerated particles to near light speeds, creating a diffuse bath of high-energy protons that heated gas through countless microscopic collisions. Unlike photons, which are easily absorbed, these cosmic rays travel vast distances, potentially distributing heat far beyond their birthplaces. Yet even this elegant solution hits a wall. The energy required would demand an impossibly high rate of early supernova, far exceeding what the infant universe's star formation could support. What makes this mystery so critical is its ripple effect. If the intergalactic medium stayed hot longer than expected, it would have stifled the growth of smaller galaxies, whose feeble gravity couldn't pull in scorching gas to form stars. This might explain why some regions of the early universe seem underpopulated, their potential snuffed out by a heat bath they couldn't escape. It also reshapes our understanding of reionization. Hotter gas resists ionization, meaning the cosmic fog might have lifted in fits and starts, not the smooth transition we once envisioned. Perhaps the most unsettling possibility is that we're missing a fundamental energy source entirely, something that operated only in the universe's infancy, leaving no trace except this residual heat. Every unexplained degree in those ancient gas clouds is a clue, a whisper from an era when the cosmos played by rules we're only beginning to glimpse. And as telescopes probe deeper into this overheated dawn, one thing becomes clear: the early universe didn't just warm up gently, it burned. In the vast cosmic kitchen of the early universe, most hydrogen clouds were either too hot to clump together or too diffuse to collapse, except for a handful of strange outliers. These cosmic Goldilocks zones struck the perfect balance, not too hot, not too cold, but just right for star formation to ignite against all odds. Their existence poses a tantalizing question: how did these rare pockets of ideal conditions emerge in a universe that was, by all accounts, wildly inhospitable to such perfection? The standard story goes like this: after the Big Bang, the universe expanded and cooled, leaving behind a nearly uniform sea of hydrogen gas. Tiny quantum fluctuations from inflation created slight density variations, some regions marginally denser than others. Gravity amplified these differences over time, with the denser spots pulling in more gas until they collapsed under their own weight, birthing stars. But here's the catch: the math suggests most gas should have been just shy of the critical threshold for collapse. The universe's expansion was stretching matter apart faster than gravity could pull it together, like trying to build a sandcastle as the tide rushes out. Yet somehow these Goldilocks clouds defied the odds, crossing the line into star-forming territory when their neighbors couldn't. One clue comes from their peculiar temperatures. While most hydrogen in the early universe hovered around 10,000 degrees too hot to easily condense, these special clouds registered a chillier few hundred degrees. That might not sound like much, but in cosmic terms, it's the difference between a roaring bonfire and a snowbank. cooler gas moves slower, making it easier for gravity to corral atoms into dense knots. But what caused the cooling? Dark matter might hold the answer. If certain dark matter particles interacted with hydrogen, even weakly, they could have acted like cosmic refrigerants, sapping heat from select gas clouds and tipping the scales toward collapse. Another piece of the puzzle lies in the cloud's chemical purity. The first stars formed from hydrogen and helium alone, no heavier elements to help radiate heat away. Yet spectroscopic studies of ancient quasars reveal some Goldilocks clouds contain trace amounts of lithium, a fragile element easily destroyed in stars. This suggests these regions might have been pre-cooled by exotic processes, like interactions with cosmic background radiation or even primordial magnetic fields subtly steering gas into stable configurations. The most compelling evidence comes from their distribution. These just right clouds aren't scattered randomly, they cluster along the faint filaments of the cosmic web, as if strung along invisible threads. Simulations show dark matter's gravitational pull could have funneled gas into these narrow highways, creating localized pockets where density spiked high enough to overcome universal expansion. Think of it like water beading on a spiderweb. The threads themselves are nearly invisible, but where droplets gather, their weight reveals the underlying structure. What makes these Goldilocks zones so pivotal is their role as cosmic matchmakers. Without them, the first stars might have been delayed by billions of years, throwing off the entire timeline of galaxy formation. Their existence hints at a universe far more nuanced than our models predict, one where subtle, unseen forces conspired to turn the improbable into the inevitable. Every just right cloud we discover is a reminder that the cosmic dawn wasn't just a backdrop for creation, it was a stage meticulously set for light to emerge. Imagine a particle so elusive it can pass through a light year of lead without slowing down, a cosmic phantom slipping through matter as if it weren't even there. Neutrinos, born in the furnaces of the Big Bang and stellar explosions, outnumber atoms in the universe by 1,000,000,000 to 1. Yet for all their abundance, these ghost particles have long been dismissed as background noise in the story of cosmic structure. Now, cutting-edge simulations reveal they may have been puppeteers in the shadows, subtly tugging at the fabric of the early universe in ways we're only beginning to understand. The conventional view pinned galaxy formation squarely on dark matter's shoulders, its gravity sculpting gas into galaxies like an invisible hand kneading dough. But there's a problem. When astronomers compare supercomputer simulations to actual observations of the cosmic web, the real universe shows slightly smoother structures with fewer dense galaxy clusters than predicted. This discrepancy, known as the small-scale crisis, has led scientists to reconsider neutrinos' role. Though individually feeble, their collective mass, spread across unimaginable numbers, could have exerted just enough gravitational influence to smear out dark matter's clumpiness. Picture trillions of particles, each weighing less than 1/1,000,000th of an electron, together acting like a cosmic eraser, subtly smoothing the universe's primordial wrinkles. What makes this revelation startling is the timing. Neutrinos from the Big Bang race through the infant cosmos at near light speed for millions of years before slowing enough to cluster under gravity. During this ultra-relativistic phase, their pressure waves created microscopic ripples in space-time ripples that may have carried away just enough energy from dense regions to prevent small galaxies from forming. This could explain why we see fewer dwarf galaxies orbiting the Milky Way than simulations predict. The ghosts, it seems, were quietly pruning the cosmic tree before it could fully branch out. The smoking gun lies in the cosmic microwave background's faint polarization patterns. Certain anomalies in this afterglow, particularly a mysterious dip in power at small angular scales, align eerily well with models incorporating massive neutrinos. Even more telling is the distribution of Lyman alpha forest absorption lines, the fingerprints of hydrogen gas clouds along quasar sightlines. Their spacing suggests the universe's gas was distributed more evenly than dark matter alone would allow, as if some unseen force had gently stirred the pot. Yet the plot thickens when we consider neutrino flavors. These particles come in three types: electron, muon, and tau, and can oscillate between them mid-flight. If one flavor interacts differently with dark matter or ordinary matter, it could have created asymmetric feedback loops during galaxy formation. Imagine a neutrino wind blowing preferentially in certain directions, herding gas into specific configurations while leaving other regions sparse. Some theorists even speculate that sterile neutrinos, a hypothetical fourth flavor, could have triggered early dark matter collapses, seeding galaxies in unexpected places. The implications rewrite more than just astrophysics textbooks. If neutrinos played referee between dark matter and visible matter, it means the universe's structure wasn't dictated by gravity alone. Their subtle interventions might explain why some galaxies stopped growing prematurely, or why certain voids in the cosmic web appear emptier than they should. Upcoming experiments like the Vera Rubin Observatory and the Deep Underground Neutrino Experiment aim to measure these effects with unprecedented precision, potentially uncovering whether neutrinos tilted the scales during the cosmic dawn. What emerges is a new paradigm, one where the universe's grand architecture wasn't built by dark matter's brute force alone, but refined through the whisper-thin touch of particles we're still learning to detect. Every neutrino passing through your body right now carries echoes of that ancient influence, a reminder that even the faintest things can leave lasting marks on the cosmos. Most cosmic eras fade gradually, but the cosmic dawn didn't just dim. It slammed shut with the force of a collapsing star. For hundreds of millions of years, the universe had been waking up, its first stars flickering to life and galaxies assembling in the void. Then, seemingly overnight, the epoch ended. The fog lifted, the last neutral hydrogen surrendered its electrons, and the universe became transparent. But the trigger for this grand finale remains one of cosmology's fiercest debates. Did some universal threshold get crossed, or was it a patchwork of local fireworks that collectively burned away the darkness? The answer doesn't just reveal how the universe turned the lights on. It exposes the fragile balance between chaos and order in cosmic evolution. One camp argues for a universal tipping point, a moment when the cumulative radiation from galaxies and quasars reached critical mass, flooding the cosmos with enough ultraviolet light to ionize every last hydrogen atom. Picture a room full of candles. Each flame contributes heat, but only when the temperature crosses a specific threshold does the entire space ignite. In this view, the cosmic dawn's end wasn't an accident, it was physics' inevitability. Supporting this is the surprising uniformity of reiyonization's aftermath. The universe didn't just become transparent in isolated bubbles, but everywhere at once, as if responding to a synchronized command. The cosmic microwave background's polarization patterns seem to agree, showing a sharp drop in neutral hydrogen signatures that aligns with the predicted timing of this global transition. But there's a problem. Recent deep field observations from the James Webb Space Telescope reveal stubborn pockets of neutral hydrogen lingering long after the supposed end of the cosmic dawn. These cosmic holdouts clinging to their ancient fog suggest the process was messier than a clean universal threshold. Instead, the alternative theory posits a domino effect, localized chains of ionization where one galaxy's ultraviolet outburst would trigger neighboring galaxies to ignite, creating expanding waves of clarity like firefronts sweeping through a forest. Simulations show these waves could have collided and merged over time, stitching together a transparent universe from countless smaller events. The most compelling evidence comes from quasar spectra, which show alternating bands of ionized and neutral gas along the same line of sight, proof that reionization progressed unevenly across space. The wild card in this debate: supermassive black holes. These cosmic engines, voraciously consuming matter and spewing radiation, could have acted as universal arsonists, their jets punching holes in the hydrogen fog long before smaller galaxies had mustered enough starlight to contribute. Some quasars dating to the cosmic dawns in-game show bizarrely high ionization levels in their vicinity, as if they were chiseling through the universe's last stubborn shadows with blowtorch intensity. Yet even their power had limits. Their narrow beams couldn't have illuminated the entire cosmos alone. This leaves astronomers wrestling with a hybrid possibility. Perhaps black holes ignited the first sparks, galaxies fueled the broader flames, and only when their combined efforts reached a critical density did the final curtain fall on the cosmic dawn. Why does this ancient real estate dispute matter today? Because the epoch's messy conclusion imprinted itself on everything that followed. The timing and unevenness of reionization dictated where galaxies could form, how black holes grew, and even where life's raw ingredients ultimately settled. A universe ionized uniformly would have cooled differently, potentially stifling star formation in regions that today brim with galaxies. Conversely, a patchy, chaotic in-game might explain why some corners of the cosmos remain eerily empty, their gas too disrupted by early radiation to coalesce normally. Even the cosmic web's filamentary structure bears scars from this battle, with some voids showing traces of primordial ionization fronts that pushed matter into new configurations. The most tantalizing clue lies closer to home. Our Milky Way's oldest stars contain chemical signatures hinting they formed during reionization final throes, their atmospheres polluted by metals from the first supernova. These ancient suns are time capsules preserving a record of the cosmic dawn's chaotic last act. Studying them reveals something startling: the epoch didn't truly end. It just transformed. The same ultraviolet radiation that cleared the hydrogen fog now keeps the universe transparent, a torch passed from the first stars to their descendants. Every galaxy, every star, even the screen you're reading this on, exists because that delicate balance held, not with a whimper but with a bang we're still learning to hear. So there you have it, 25 mind-bending mysteries from the cosmic dawn era, each one a thread in the universe's grand origin story. From the birth of the first stars, those monstrous population Roman III giants, to the explosive spread of metals that seeded the cosmos with the ingredients for life, every puzzle we've uncovered forces us to rethink the universe's earliest chapters. The cosmic dawn wasn't just a transition. It was a revolution, a period of chaos and creativity where the fundamental rules of structure, light, and matter were being written in real time. Consider how much hangs in the balance. If we crack the code of those first galaxies, how they assembled so quickly, why some burned too bright while others never ignited, we could rewrite the story of dark matter itself. Those ghostly filaments of the cosmic web, the unexplained alignments of ancient quasars, even the phantom galaxies hiding in the shadows, they're all breadcrumbs leading us toward a deeper truth. And let's not forget the black holes that defied logic, growing to impossible sizes overnight, or the dark stars that might have lit up the universe without fusion. Every one of these enigmas is a paradox waiting to be unraveled, a key that could unlock entirely new physics. But here's what's really thrilling: we're not just piecing together the past. Solving these mysteries would reshape our future understanding of everything. Imagine confirming that dark matter isn't just an invisible scaffold but an active participant in cosmic evolution. Picture proving primordial black holes exist, lurking from the Big Bang itself, or that neutrinos subtly shape the destiny of galaxies. Each discovery wouldn't just fill a gap in our knowledge, it could redefine how we see the universe's fundamental forces. And the best part, this golden age of cosmic detective work is just beginning. The James Webb Space Telescope is peeling back layers of the early universe we've never seen before. Upcoming observatories like the Square Kilometre Array will listen for whispers from that ancient hydrogen fog. Every new tool, every fresh observation brings us closer to answers, and inevitably closer to even bigger questions we haven't even thought to ask yet. So now it's your turn. Which of these mysteries keeps you up at night? Is it the missing metal-free gas, the bizarrely aligned quasars, or the dark stars that might still be hiding in the data? Drop your favorite theory in the comments, because the cosmic dawn isn't just a story for scientists. It's a puzzle for all of us to solve, one clue at a time. And who knows, the next big breakthrough might start with an idea from someone watching this video. After all, the universe didn't reveal its secrets easily back then, and it's not about to